I'm Don, N4DJ, and I'm going to talk a little bit about beverage antennas. The beverage was developed by H. Beverage, Chester Rice, and E.W. Kellogg back in the 20s. There was a QST article in November 1922 by H. Beverage, and this regional beverage article was reprinted in January 1982 QST. Now, what is a beverage? A typical beverage is a long single wire about 8 feet above the ground. It's sensitive to vertical polarization. It's directed off the end and not broadside. There are many forms of the beverage. It can be a long single wire above ground. It can be 2 wires or multi-wires above ground. It can be terminated with a resistor. It can be unterminated. Or it can even be a simple wire just laying on the ground. As a matter of fact, I believe the first beverage was such an antenna. Now, the theory of the beverage. The incoming wave in line with the wire induces current in the wire. Current builds up in the wire to a maximum at the receiving end. Now, signals from the opposite direction will build up at the opposite end of the antenna from the receiver, and they are usually dissipated in a resistance. Now, the theory says that if the electric field is at right angles to the wire, no signal is induced. And that's one of your electrical laws. The beverage would not work in this case. Now, this diagram shows a E field at perpendicular to, at right angles to the receiving antenna. So if a signal was coming down the wire with the E field perpendicular to the wire, you would never hear anything. However, the E field must be at some angle other than a right angle with the wire to induce current. An incoming sky wave will have such an E field, and a wave over an imperfect conductor, such as real ground, will also have such a field. Now, this shows an E field at other than a right angle, and you will see there is a vertical and a tangential component to the E field. This E field is slanted forward as it goes down, sweeping the beverage antenna wire. Let's look at an incoming wave moving along the wire and see what happens. Okay, this is a diagram of a waveform with a tilted electric field sweeping down the beverage wire. If the wavefront sweeps along the wire, current will be induced in the wire by the component of the E field that is parallel to the wire. Now, what we're looking at in this diagram is the tangential component of the E field, EX1 plus EX2 plus EX3 plus EX4 and so on. These induced currents add up and they are traveling down the wire slower than the actual E field is sweeping the wire. Now, what we have is the sky wave and the induced signal in the wire are traveling at different speeds. These signals in the wire will continue to add up until the signal in the wire starts to lag the incoming sky wave by 90 electrical degrees. At that point, the incoming sky wave will start to decrease or cancel the signal that is propagating down the wire toward the receiver. The difference in speed depends mostly on the ground and the height of the wire. The ratio of the two speeds, the speed of the radio wave and the speed of the conducted current in the wire, is the velocity factor, just like in coax or any transmission line. The typical velocity factor for a standard beverage or wire 10 foot above the ground is about 90%. We can easily calculate the length of wire where we'll get the maximum signal strength. That is the length where the induced signal lags the incoming wave by 1/4 wave or 90 degrees. Now this is a formula to calculate the length in terms of wavelength and velocity factor. And this is at a 0-degree elevation angle. Now this example uses a wavelength of 540 feet for 160 meters, velocity factor of 90%, which is pretty average. And we come out with a length of 1,216 feet. And many people have used the term a 1,200-foot beverage. 1,200 is just a typical length for a 160-meter in-the-air beverage. Now these are some examples of typical lengths for beverages for 160, 80, and 40 meters. For pretty much the same performance, you'd have a 1,200-foot beverage on 160, or maybe a 600-foot on 80, or 300-foot beverage on 40 meters. Now, right now, you're probably thinking, this doesn't apply to me. Well, it doesn't apply to me either. I don't have 1,200 foot for a beverage. I don't have 600 feet for a beverage. In fact, right now, I don't even have 300 feet for a beverage. So the question is, what can somebody do if they don't have 300 foot to string out a beverage? Well, really, there's quite a few things you can do. For any given wavelength, the velocity factor is the main element in determining the maximum effective length. Now, to remember the formula, this formula uses velocity factor. Now, I've run the numbers in the formula. For a 0-degree wave angle, velocity factor of 90 degrees, you have a 1,215-foot antenna. If the velocity factor goes down to 75, the antenna length calculates out to be 405. For a 50% velocity factor, you're looking at a 135-foot length of wire. So now we're bringing the length of the wire down significantly. Now, what about the elevation angle? I was saying that all the formulas were for a 0-degree elevation angle. Well, if you want to use a practical elevation angle, such as 10 degrees, the formula gets a little bit more complicated. The alpha in the formula would be your elevation angle or your takeoff angle. Now, back to the same chart we had a minute ago. If you're looking at a velocity factor of, say, 75 degrees, you would be looking at a maximum effective length of 405 feet at 0-degree takeoff angle. But if you accept the fact that you're probably going to receive signals from 20 degrees, then the optimum length for receiving signals from a 20-degree elevation angle with a velocity factor of 75 would be 343 feet. So now, what is practical? We often have to settle for less than the optimum length, and there are also some things that we can change. If we back off a little bit from a 0-degree elevation angle, which really isn't practical anyway, and we drop the wire to the ground where we can decrease the velocity factor, even though we're not going to receive quite as strong a signal as we might have with a wire up in the air, we're still going to get enough signal on 160 meters to hear the DX stations. And we're not really going to lose that much, as I'll show you here in a minute. Now, what if the velocity factor was 75%? That means on 160 meters, what would have been a 1,200-foot beverage becomes a 400-foot bog. On 80 meters, a 600-foot beverage becomes a 200-foot bog. 300-foot beverage on 40 meters becomes a 100-foot bog. So we've really streamline these antennas by just laying them on the ground. Now we also need to remember one other thing. Most beverages are not 1,200 foot long. 1,200 is just the maximum effective length, and it's definitely not the minimum length. Likewise, our calculated 400 feet is just the maximum effective length for a 0-degree elevation angle when the velocity factor is 75%. Of course, now, how do we change the velocity factor? Well, what does determine the velocity factor? Mostly, it's the height of the wire above the ground. Also, the composition of the ground becomes more important as you get closer to the ground. The composition of the ground is not quite as significant as the height above ground. So let's ask the question one more time. How do you change the velocity factor from 90% to 75%? Very simple. Run the wire on the ground. Does it work? Yep. It defies our normal HF thinking. We always want higher antennas. We think we need more gain, stronger signals. Why does it work? Well, signals on 160 and 80 meters are not as weak as we tend to think. They're usually simply covered up by the noise. If we can reduce the noise, we will hear the signals. Okay, think about it. Suppose we have 3 noise sources, one each from a different direction, one from the north, one from the south, and one from the west. And our desired signal is from the east. We can't hear it because of the 3 noise sources. What happens if we remove or reduce the 3 noise sources? We now hear the signal with little or no noise. General band noise comes from all over, every direction. We need to reduce it from all directions except the one desired direction. Directivity is the key to receiving, not gain, particularly on 160 meters. We only need the signal to be above the noise. An S2 signal with no noise is much better copy than an S7 signal with noise at S9. Now here are 2 conventional Beverage plots. The elevation or takeoff angle is 20 degrees, and these are 2 10-foot high Beverages, one 1,200 foot long and one 480 foot long. Now there are some differences in the 2 Beverages. The longer Beverage has more gain, which means a louder signal off the front. They both reduce the signal off the back and sides. The long one is better, but the short one still works very, very well. Now let's take a look at a short bog. This is a 180-foot bog constructed by K5 VIP. This is the plot for the elevation angle of 20 degrees. And this shows the pattern. Now, the night after K5 VIP put up, or maybe we should say put down, his bog, he reported to me that he heard a station in Europe on 160 meters, loud and clear, that was barely copyable on his regular 160 meter antenna. So this was definitely worth doing in his case. Now, this is a plot of my European bog. It was 220 foot long, running northeast southwest. The elevation angle is 20 degrees. This was a very, very good antenna in my opinion. Now the results of my 220 foot bog pointed toward Europe. It resulted in many stations in Europe in both the ARRL and the 160 meter contest. In fact, after the 160 contest, DJ7 Whiskey wrote to me, "Hi Don, I'm lucky you built your bog for Europe. We made a QSO during the CQ160 and you copied me first call with my 5 watts. I thought that was nothing short of fantastic." I also had a 480 foot bog, and this compares my 480 foot bog to K5 VIP's 180 foot bog. Notice that the 480 foot bog has more gain, maybe about 8 dB, and it has a little bit better front-to-back ratio. But basically, both antennas are directive, and the 480 foot bog was really optimum, I thought, for 160 meters. Now this is an interesting plot. It's a 480-foot beverage, 6 foot high, in a bog, 480 foot, laying on the ground. Now what we notice here is that the in-the-air beverage has almost 2 dB more gain. That's not a whole lot, really. The bog actually has a better front-to-back ratio. Signals from the front are less than 2 dB weaker, but off the back they're down by over 5 dB. Okay, so let's talk about bog construction for a minute. Bogs are pretty simple. You run a wire as long as you can, straight as you can, on the ground. 100 to 500 feet will work, and work quite well. Obviously, the longer lengths are a little bit better than the shorter lengths. 220 feet and 480 feet work really well. I've had very good luck with bogs, those lengths. And remember, length is not critical. What is important is that you have a ground rod at both ends. I use a standard copper-clad ground rod cut in half. In my opinion, a really good ground is not necessary. In fact, I told one person who didn't have a ground rod to use a long screwdriver, and he tried it and it worked. He eventually got to the hardware store to get himself a real ground rod, but the screwdriver will work in a pinch. Now the wire is directional away from the feed point. So feed it on the southwest end, run it northeast, and you have a European bog. Connect a resistor somewhere between 160 to 300 ohms between the end of the wire and the ground rod. Now you must use a simple transformer to feed the beverage. The ratio must match about 300 ohms to 50 or 75 ohms, depending on your feed line type. I use a 75 ohm RG6 coax and an impedance ratio of 4 to 1 for a 220 foot bog seem to work just fine. These ratios are not necessarily critical. You just have to be in the ballpark. For the transformer, I recommend binocular cores. They cost like 75 or 80 cents each. Could be as much as $1 by the time you pay postage. They're very easy to wind. I use a 4-turn primary and an 8-turn secondary of number 28 wire. You can also use a 2-turn primary and a 4-turn secondary. Yeah, this just happens to be a picture I took of my transformer that I used on my 480-foot western bog. And you can see its size relative to a quarter. Now this is the feed point of my northeast bog. The transformer is in an electrical connection box, which is screwed to a stake in the ground. Yeah, this is an identical transformer enclosure. This was for my west bog. At one time I was using a 7.56 to 1 ratio. Can't remember exactly why I was doing that. Now this was in the testing phase of one of my first bogs. You can see the ground rod. The transformer is in a like a Tupperware container. I'm using alligator clips to make the connections, and it worked. This is an older type of transformer before I went to binocular cores and using a few terminal strips and a transformer in a box. Okay, the results of these bogs. They work. They really work well. I worked both the 160 CW and sideband contests this year, 2013. 831 Qs on CW and 529 Qs on single sideband. I only use my 2 bogs and my 1 in-the-air beverage for receiving. I worked 22 countries on 160 in the ARRL 160 contest, listing only on the beverages. Even if you don't work 160, bogs work very well on 80 and 40 meters. A good bog length for 80 meters is only half what you need for 160. A 150-foot bog works on 160. It works even better on 80 meters. Now here are some of the velocity factors that I measured at my particular location. I have a gravel driveway, backyard grass, woods near the end of the northeast bog, and woods near the feed point of the northeast bog. The velocity factor I calculated was 0.65 on the driveway to 0.77 in the woods near the feed point of the bog. So we're looking at a velocity factor of maybe 0.72 to 0.77 underneath my all my bogs. Now you can get more information on bogs from N4UN's Low Band DXing 5th edition. I don't recommend the early editions because they have some bad information on beverages. But the 4th and 5th edition seems to be spot on with transformers and beverage configuration. Also, the ARRL antenna book is a very good resource, as well as several other textbooks and QST articles by H.H. Beverage.